Alright, so even though parametric equations are kind of an advanced topic usually, surprisingly, we're going to use an Algebra 1 technique to convert from parametric equations to rectangular, and that is substitution. So just like if you had a system of two equations and two unknowns, you'd want to use substitution or elimination to get rid of one of the variables and condense stuff down into one equation. That's exactly what we're going to do here. So you'll see what I mean. Let's get started. So all we need to do basically is solve one of the equations for t and then plug that in to the other equation. Now usually you're going to want to solve the x equation for t and plug that in. So in this first pair, this is actually two separate example problems, in case that's confusing. So x and t are the same thing, right? X equals t. So that means anywhere we see a t, we can put an x. And oh, look at that. I see a t right here. So let's just plug in x for that t, and we'll get y equals x cubed. Pretty sweet, huh? Now, as I mentioned in the previous video, these parametric curves have a direction and stuff. When you eliminate the parameter, we're going to lose some information. Don't worry about it. The point is that this cubic has the same graph as this one. Pretty exciting stuff, I know. It'll be a little bit harder. Well, you'll see in a minute there can be some harder ones, but it's basically this straightforward. So here's another one. We got to solve for t, so I'll subtract 1 from both sides, and that'll give us that t equals x minus 1. And now, since that's what t equals, you just plug it in right here. So you just get y equals x minus 1, since that's what t was, and we keep the exponent of squared. Pretty nice, pretty easy. That's usually how it goes. Now this one looks a little bit uglier because there's an absolute value, but again, don't worry about it, since we'll solve for t in an equation that doesn't have an absolute value. So in this one, divide both sides by 3, and you'll get that t equals x over 3. And then we'll just plug that in right here. So we'll get that y equals the absolute value of x over 3 plus 1. And you could either be done right now, or if you have one of those books or teachers that likes to simplify stuff, I've also seen this type of problem. What they'll want to do is sort of just have x plus 1 in the absolute value. And the way to do that is you got to make this into a 3 and put a 3 down here. These are algebraically identical, so I guess the way we could have done this to make it more obvious would be x over 3 plus 3 over 3, just to get a common denominator, which gives us x plus 3 over 3, and then they say, hey, you know what, that 3 can't be negative anyway, it's just a 3, so let's just go ahead and put the absolute value only around the x plus 3. And that's kind of a nice thing to do just because it makes it more obvious what the graph would look like. If you know how to graph parent functions and transformations and stuff, you would say, oh, look at that. That's an absolute value. So if this was y equals this stuff, then that's an absolute value v shape, multiplied by 1/3, which makes it a lot flatter a v, and then it's shifted to the left 3. So that's the advantage of writing it in this form instead of this form. But either way, once again, we just solved for t. Got t in terms of x, and then plug that in for t in the y equation. All right, this one looks a little bit trickier, right? Because if you wanted to solve either one of these for the parameter, which is theta, you'd have to do an inverse trig function. So you might be thinking, hey, if I wanted to solve for theta in the top equation, I'd get like x over 2 equals secant theta. Now I got to do an inverse secant on both sides in order to get theta by itself. I could do the same thing here, and I'd have to do an arc cosine of both sides. So I'd get that theta equals arc cosine of y or something crazy. Turns out that's too much trouble, and if you get off in those arctangent, inverse tangent things, you're almost always doing it, you're missing a trick, is what's going on. So it turns out that what you really want to do is take a step back and look at these two equations and say, can I think of any identities or any ways that I could mix and match and substitute the two without actually having to undo the trig functions? And the keen observer will notice that a secant is actually a 1 over cosine. So these both equations involve cosine theta, which means we could just get cosine theta by itself and sub in that way. So what we're going to do is the top equation we're going to rewrite as x equals 2 over cosine theta, just by rewriting that secant as 1 over cosine. And now you'll notice we have a cosine theta right here, and we know that y equals cosine theta. So what we can do is just replace the cosine theta with y. and you're either done at this point or you're thinking to yourself, my teacher really likes things, y equals some stuff, like a function of x instead of a function of y. So we might just multiply both sides by y and divide both sides by x, and then you'll just get y equals 2 over x. So without doing any inverse trig functions, we're able to get to that. And that seems like that's usually the trick. If you're converting parametric equations that have sines or cosines or secants in them, the trick is almost always to do something clever, either use an identity or do what we just did there. Technically that was an identity, the fact that secant is 1 over cosine. But you're looking for little tricks like that to avoid doing inverse trig functions. Alright, so in that last one we just had to recognize that cosine was in everything. And something that has both sines and cosines in it, like where sine is in either x or y, and cosine's in the other one, then if you're experienced with these, and you've seen a video about conic parametric equations that comes up after this video, then you'll realize that this is the equation of a circle, or an ellipse if there was a coefficient in front of one of these, which would just be a stretched out circle. But you don't actually need to know that or need to memorize that in order to convert stuff that has sines and cosines. There's a trick I want to show you because this happens so often where you have sine in one and cosine in the other. It's sort of like a special category of problem that every teacher uses. The trick is we're going to square both equations. So anytime you see a sine in one of them and a cosine in the other, you almost always want to square both equations, and I'll show you why. Well, what is so great about sine squared and cosine squared? They're in that identity, right? That classic trig identity, sine squared plus cosine squared equals 1. So if we square both equations, so now we'll have x squared equals sine squared, and y squared equals cosine squared. By the way, for keen observers, normally cosine would be in the x equation and sine would be in the y equation, but it doesn't matter for a circle. It'll just end up still being a circle. And once we square both equations and we add them together, because hey, in algebra, any two equations you see, you can add them together if it suits you. So now we have sine squared plus cosine squared, and look at that. That's our identity. So the answer is x squared plus y squared equals 1. And that's a trick you can use when sine and cosine are both in the same problem. Now let me throw a slight variation at you. Let's say they'd give it x equals sine theta, but then y equals, I don't know, like 3 cosine theta. At this point, squaring is still what we want to do, but there is one step before we square both sides. Here's the problem. If I just squared both sides right now, I'd have a sine squared in one and a 9 cosine squared in the other. And there is no identity for sine squared plus 9 cosine squared. The coefficients need to match. So if I have a 9 cosine squared, I better have a 9 sine squared to go with it so I can factor out the 9 and my identity still works. 8 and 9 doesn't work, 1 and 9 doesn't work. We got to have the numbers match. So the trick is, before we square this top equation, we're going to multiply both sides by 3 in order to get a 3 in front of the sign. So now when we square both equations, we'll have 9's on the right side of both. So when we square this out, that top one becomes 9x squared equals 9 sine squared theta, and the bottom one is just a single y squared equals 9 cosine squared. Now when we add the two equations together, you'll notice on the left we have two different, so it's not like we totally cheated and just manufactured a 9, because you'll notice that now on the left side we have 9 of one thing and only 1 of the other. Where if this had been a circle or something, we'd have the same coefficient in front of both x and y. So 9x squared plus y squared equals, and now we've got 9 sine squared plus 9 cosine squared, which by now you guys probably realize is just going to be 9. So there's our equation. 9x squared plus y squared equals 9. You notice this looks a lot like a circle, just not quite, and that is correct. If you recognize this, it's actually an ellipse. Because the difference between a circle and an ellipse, they both have x squared plus y squared, but an ellipse gets stretched a little bit in either x or y direction by putting a bigger coefficient in front of one of the two variables. So anytime you have what looks like a circle, except there's different coefficients on the x squared and y squared, that's an ellipse instead of a circle. And the standard function of an ellipse would be that you want a 1 on the right. Like we'd rather replace this 9 with a 1. So we'll divide everything here by 9 to get it in standard form, and we'll get x squared over 1 plus y squared over 9 equals 1. So that would be the standard form of an ellipse. Seems like most teachers would not take points off for not getting 1 on the right. Depends which chapter you're in. But so, moral of the story, anytime you're converting things that have both sine and cosine in them, like sine in one of the equations and cosine in the other, squaring both sides to get this identity is the key. And then if you have a coefficient in front of one, like this 3, then that means we got to manufacture a 3 in front of the other one so that the sines and cosines have the same coefficient in front of them. All right, last one. So this one's again an identity. And also it's got a little bit of trick to it that we've got an interval. So all that means is that instead of using the entire curve, we might just have part of it. But of course, first things first, we got to figure out what this thing even looks like. So, just looking at this, I'm reminded of another one of our Pythagorean identities, which is that tan squared plus 1 equals secant squared. So I'm thinking that maybe there's a way that we could get this equation to look like that. And I'm thinking the way we do it, let's see, well this one I've got a tangent squared. If I had a 1, so maybe what I should do is add 1 to both sides. So I'll get x plus 1 equals tan squared plus 1. And then tan squared plus 1 is really the same thing as secant. So replace this tan squared plus 1 with secant, so I get x plus 1 equals secant squared theta. And oh, look at that, secant squared is this, so I can just replace that with y. So my substitution ends up happening by converting tan squareds into secant squares, which I can then replace with y, since y is just secant squared. So my overall equation is y equals x plus 1. Now you'll notice that's very counterintuitive. We have a couple of squared things, and they ended up just being the equation of a line. Kind of wacky. And one thing I haven't done yet is accounted for this limitation. This is not, if I just said, hey, we have the graph of y equals x plus 1, that's a line going both directions indefinitely, right? But because there's this interval to worry about, it makes me wonder, hey, maybe we're not going to use the whole line. So what I want to do is, either using a graph or something else, I just want to figure out what portion of that line I'm going to get. Now if you just look at this interval, that's 1/4 of the unit circle. So my first guess is that I'm only going to get 1/4 of the line. I don't know if that's true or not, but let's take a crack at it. So the way we'll do it is, we know it's a line x plus 1, so we'll just try plugging in 0 each end of the interval and just figure that it includes everything in between. So if you plug in 0 here and here, we'll get x equals the tangent of 0, which is 0, squared is 0. So we get x equals 0. Our starting point, oops, I don't know if that's 0 or not. Our starting point is x equals 0, and y would equal 1 if we plug in here, because the secant of the cosine of 0 is 1, 1 over 1 squared is also 1, so 0 comma 1. Or we just take that 0 and plug it into our final equation, because if you plug in 0 right here, you get 1 out for y. So our starting point is 0 comma 1, which happens to be the y-intercept as well. And then we plug in pi over 2. The tangent of pi over 2 is, infinity. X equals infinity. That's weird. So the endpoint I'm getting is infinity, and the y-coordinate is also infinity, because the secant of pi over 2 is infinity. And of course, if you square infinity, you still have infinity. So this didn't help us much, did it? I've got the start point of the line. I know we're going to follow the equation y equals x plus 1, which is just a 45-degree angle there, slope 1. So what do I know? Am I done here at this point? Yeah, I am, because even though infinity comma infinity cannot be graphed, we do know that that's basically saying, you know what? This thing goes up and to the right forever. So it turns out that this graph is just half the line. It's like a ray starting at 0 comma 1 and going that way. So our equation, it just gives us the right side of the line, and it's going in that direction to the right. So there you go. That's identities with intervals. But the moral of the story remains the same. We're looking, anytime you have trig functions or something tricky like that, you're looking for some way to link the two equations together. If they have squared trig functions in them, you're probably looking to use an identity. If they have non-squared trig functions, like sine and cosine, you're probably going to square them, and again, use an identity. And then like that first problem we did, if nothing is squared, but they both have a cosine in them, for example, if one had cosine and one had secant, you'll be looking to rearrange the equation and do some substitution. All right, so that's converting parametric to rectangular. A little bit more straightforward. In the next video, we'll take a look at converting rectangular to parametric, which is either easier or harder, depending on how you look at it.